Now, as an aside, you should be aware that it is possible to exhaust smoke from the compartment of fire origin itself without having the smoke spilling into the atrium, as you can see here. In such a case, we would be using the simple plume methodology within the room of origin to calculate the required volumetric extraction rate required to keep the smoke higher than the downstand at the shop front. But we are looking at complex plumes here, so we'll leave that to the simple plume section and we'll move on to examine complex plumes further. Having calculated how much smoke is coming out of the opening using one of the models, we can now look at how the smoke behaves from this point on and examine our options for dealing with it. If there is no ceiling outside the opening and the smoke spills straight up into the smoke reservoir, then we can use one of the available spill plume models to determine the amount of smoke entering the smoke layer. We shall look at the spill plume models shortly, but first we should look at the effects if there is some sort of ceiling outside the opening under which the smoke will flow before it spills up into the smoke reservoir. It's generally found that there is negligible entrainment into a smoke layer as it moves horizontally under a flat surface. Therefore, if there's no downstand at the opening of the room of origin, so that the smoke just flows smoothly and directly out of the opening, then the amount of smoke does not increase as it leaves the opening. We call the mass flow rate of smoke beneath the ceiling outside the opening MB. This stands for the mass flow rate of smoke under the balcony. And this is because it is often the underside of a shopping mall balcony that we're looking at in such cases. So if there is no downstand at the opening, we have the equation MB equals MO. In other words, the amount of smoke under the balcony is equal to the amount of smoke that's leaving the opening. This is not the case, though, where there is a downstand at the opening, which forces the smoke to flow down beneath it as it leaves the opening. In this case, there is some additional entrainment of air as the smoke leaves the opening, and this is taken at the moment to be a doubling of the amount of smoke. More accurate models are being researched, but for the time being we use the equation MB equals 2 times MO. This gives us a prediction of the amount of smoke that will be flowing under the balcony. Now that we know how much smoke is flowing beneath the balcony, or the ceiling outside the opening, we might want to consider what to do with that smoke. If the underside of the balcony or ceiling is more than 1.5 metres from the opening to the spill edge, then it is generally found that the smoke may not have sufficient forward impetus to drive it all the way to the spill edge, and some of the smoke may start to spill sideways beneath the balcony, spreading the width of the balcony that is affected by the smoke. This sideways spread beneath the balcony is considered to be bad and it should be avoided. Firstly, it spreads the damage, and smoke may be given the opportunity to enter areas that it's not meant to, other shop units for example. Secondly, the spread out smoke will lead to a wider spill plume, and it's been found that wider spill plumes lead to greater air entrainment into the plume and therefore more smoke entering the smoke layer. The smoke will also be cooler and less buoyant. And thirdly, we have no model for predicting the extent of the sideways movement of the smoke under the balcony, and so if we allow it, we'll have no figure available for the width of the spill plume. And if we don't know how wide the spill plume is, then we won't be able to predict the entrainment that takes place in the plume as it ascends to the smoke reservoir. So where there is a possibility of smoke moving sideways under a ceiling or balcony before it spills into the smoke reservoir, it's usually contained by the provision of smoke channeling screens on each side. These will stop the smoke from spreading sideways and will direct it straight to the spill edge, where it will turn and rise into the reservoir. As the smoke moves towards the spill edge from the opening, it moves in a flowing layer, and the depth of this layer can be determined using the model shown here. dB is the depth of the flowing layer under the ceiling or beneath the balcony. CD is a coefficient, and this is usually 1 if there is no downstand present at right angles to the flow, or it's 0.6 if there is a downstand present at right angles to the flow. The subscripts B are used because we're applying this model under a balcony, but the equation can be used more generally elsewhere in premises, and at such times the subscripts will be different. MB is the mass flow rate of smoke under the balcony in kilograms per second. TB is the temperature of that smoke in Kelvin. L is the separation distance of the channeling screens. In other words, it's the width of the flowing layer. Theta B is the temperature rise in the flowing layer above ambient in Kelvin. And TO is the ambient temperature in Kelvin. Now David's going to do some examples of flowing layer depth with you.